Welcome back, everybody, to the Ham Radio License General Pool Study playlist. Yeah, that is a mouthful. You want your general license, and even more, I want you to get your general license so you can get on HF and we can make a contact in the future. We are using hamstudy.org, a free website where you can make an account for taking Technician, General, Extra, as well as some of other license systems with the FCC and even amateur radio licenses in other countries. This is the website, but I am using the app right now for this study program. The way I do this is pretty simple. I just go through the questions and we focus on the right answers and we go sub-element by sub-element. So let's dive into this. General, and we're going to click on Read Questions. If you're following along using the app, I will have links in the video description for the website and the apps as well. This is sub-element G3, meaning we're part of the way along, but we got a lot more to go. As always, take the practice exams on your own, and if you're seeing this video out of order, and you should be starting on 1, these are all on a playlist on my channel, as well as linked in the video description, so you can continue your studying that way. So diving in, sub-element G3, radio wave propagation. Every sub-element is generally broken up into sections. This one has 3 sections, and it starts off with sunspots and solar radiation, geomagnetic fields, and stability indices. Whew, that is a lot. Starting with section alpha, question 1, how does a higher sunspot number affect HF propagation? And the answer is higher sunspot numbers generally indicate a greater probability of good propagation at higher frequencies. That is even more so the case based off of the sun's 11-year cycle, which we are in solar maximum, which means there is more sunspots on the surface of the sun, which helps out with the propagation on higher frequencies. So for you technicians, as you're taking the study exam, you should get on 10 meters. It's a space that you have to do single sideband on. Question 2. What effect does a sudden ionospheric disturbance have on the daytime ionospheric propagation? And B, it disrupts signals on lower frequencies more than those on higher frequencies. So yeah, if you're on 20 meters and lower, you can get some disruptions if there is a disturbance in the ionospheric force. Question 3, approximately how long does it take the increased ultraviolet X-ray radiation from the solar flare to affect radio propagation on Earth? 8 minutes, basically traveling at the speed of light. Which of the following are the least reliable bands for long-distance communication during periods of solar low activity? And that's going to be the high frequencies. So solar maximum, high frequencies are good, but it's solar minimum on that 11-year cycle, so the low point. 15, 12, and 10 meters actually perform very badly, insofar as sometimes 12 and 10 meters are not even usable, and sometimes 15 isn't either. Question 5, what is the solar flux index? A measure of solar radiation with a wavelength of 10.7 centimeters. Now, this is a good time to actually use that explain button. As you're studying, you can use the explain button on the website and the app. So let's do that right now. Measuring solar flux is another way of expressing the amount of solar activity. The solar flux is the intensity of the sun's RF energy emissions. The solar flux index is a standardized representative of this radiation energy, which is measured at a fixed value of 2800 megahertz. Frequency is 10.7 centimeters wavelength. So yeah, gives you more context as you're reading through the questions, and that can help out a lot. Question 6, what is a geomagnetic storm? And it is a temporary disturbance in the Earth's geomagnetic field. We have a field around the Earth. It is the geomagnetic field, and when there is an effect of the sun basically spewing out some of this energy that it has, it can disturb that, which will cause radio wave propagation to change, if not shut it down in some cases. At what point in the solar cycle does the 20-meter band usually support worldwide propagation during daylight hours? At any point. So any time during that 11-year cycle, lows or high, 20 meters is going to be your go time, daytime band. How can a geomagnetic storm affect HF propagation? It will degrade high latitude HF propagation. So as higher you go up the latitudinal area, then you can get dropouts in propagation capability when there is a geomagnetic storm. Because if you think the geomagnetic barrier or field around the Earth comes out of the poles and is affected, it will be suppressed in those areas towards the higher latitudes and lower latitudes. How can high geomagnetic activity benefit radio communications? It creates auroras that can reflect VHF signals. Yeah, that's actually a kind of funky thing. Go Google Aurora VHF radio and listen to the noise that they create when you actually pick somebody up on the other end. It's pretty weird. What causes HF propagation conditions to vary periodically in 26 to 28 day cycles? And it is the rotation of the sun's surface layers around its axis. Sunspots will come back around in a 26 to 28 day cycle, and that can change the effect among many other things. How long does it take a coronal mass ejection to affect radio propagation on Earth? And the answer is 15 hours to several days. Now, Tamitha Skov looked at this or told me that's basically like the sun barfing out material. And that's an interesting way to look at it. If it's purely light, it will take minutes. But if it's barf, it's going to go a little bit slower. In that case, about 15 hours to several days. Question 12. What does the K index measure? And it's the short-term stability of the Earth's geomagnetic field. Stability is good in this case for radio operation and propagation, so K-index is something to keep an eye on. What does the A-index measure? And that's the long-term stability of the Earth's geomagnetic field. Again, something to keep an eye on. The weather of the sun, radio weather, space weather, if you will, is something that a lot of hams pay attention to. Free shout out to Tamitha Skov. She's on X as well as YouTube, and she does a really good job. Thanks, Tamitha, for giving your weather reports to Ham Nation that we play every other week. Question 14. How is long-distance radio communications usually affected by the charged particles that reach Earth from solar coronal holes? B. HF communication is disturbed. So keep that in mind, something to remember. So anytime there's a coronal mass ejection, then you can expect that there'll be some kind of effect to high frequency, that's what HF stands for, radio propagation. All right, there is section alpha. We're going to go to section Bravo now in subelement G3. What is a characteristic skywave signals arriving at your location by both short path and long path propagation? D, a slightly delayed echo might be heard. This is a fun one to think about in your head. So if we are on the United States together, I'm in California. Let's say you're on the East Coast. Going straight across and hearing each other is the short path. If I went around the Pacific Ocean and then back around the entire other half of the world and across the Atlantic Ocean, and you heard me, that would be long path propagation. Now, it's rare, but there are some situations where you will hear both short path and then long path communication at roughly the same time. But it takes time for the longer path propagation to go around the Earth and get to you via your ears, via your radio, than the short path. And so you'll hear a slightly offset audio of that individual you're making a contact with. It's a rare phenomenon, but it's kind of cool when it happens. Question 2, what factors affects the muff? And this is D, all choices are correct. There are not a ton of all choices are correct in the question pools, so when you get them, it's a kind of a gimme or a freebie. Make sure, though, that you're ready to take advantage of that. So that includes A, path, distance, and location. B, time of day and season, and C, solar radiation and ionospheric disturbances. So all of that will affect the muff. And what is the muff? It is the maximum usable frequency, meaning the frequency, the highest frequency you can use and still be able to get propagation and get your radio waves to go out from your radio into the atmosphere, wherever it's going. Question 3, which frequency will have the least attenuation for long-distance skip propagation? And it's A, just below the muff. So if the maximum usable frequency is, I'm just throwing out a number, 28.400 megahertz, right in the middle of the technician portion of 10 meters. If you go just below that, you're going to have the least attenuation long-distance skip propagation, which is good. You want to do that where possible, assuming that's what you're aiming for, the longest distance type stuff. Keep in mind the muff, and also we'll see a little bit later, the lowest usable frequency, or the LUF, will be part of something you can consider for long-distance communication. Question 4, which of the following is a way to determine current propagation on desired band from your station? A, use a network of automated receiving stations on the internet to see where your transmissions are being received. I like to use the mode WSPR, WSPR. It transmits a digital signal from my location, and it populates a map of every station that heard my signal that happens to be uploading reports. This is a really handy way to determine which bands of operation, which frequency, and also which antennas, because I have a couple of antennas, are getting out the best for whichever band of operation I want to use. So consider using WSPR. How does the ionosphere affect radio waves with frequencies below the muff and above the luff? And the answer is A, they are refracted back to Earth, and that's what gives us that beyond line of sight signal propagation. We want that for HF radio. You notice there's a lot of questions regarding high-frequency radio because that's what you're picking up. You're picking up bands for HF operations. So we want to know how to get our signal out the furthest, and by maximizing the use of the muff and luff reports, we can do that. Question 6, what usually happens to radio waves with frequencies below the luff? The answer is C. They are attenuated before reaching the destination. So you're using a lower than the lowest usable frequency. Doesn't mean that they're shut down completely, but it does mean that they're attenuated in either being absorbed by the atmosphere or other things that might be happening. But just keep in mind that you want to generally maximize your space by using something between the muff and the luff at all times for the most effective radio communication. What does the luff stand for? You already heard it. A, the lowest usable frequency for communications between two specific points, the luff. What does the muff stand for? The maximum usable frequency for communication between 2 points. Question 9, what is the approximate maximum distance along the Earth's surface normally covered in one hop using the F2 region? Now, you're going to hear a lot about different layers of the atmosphere, and depending on how you look at angles, that is going to change kind of how far you can get out, and hopefully you either draw something out on a paper towel. Why a paper towel? I don't know. Piece of paper. You can upgrade to a piece of paper for this. But where those layers are and the frequency that you're operating on is going to change the maximum distance that you can achieve. With the F2 region, you can get C, about 2,500 miles. Let's click explain and see what we hear here. Hey, let's see. The F2 region is the highest region of the ionosphere, which is our sweet spot for long-distance skywave transmissions. The F2 is highest during the middle of the day when the sun's energy is the greatest. It gets even better during periods of high solar activity, like we are right now, and high ionization of the upper atmosphere. The approximate maximum distance along the Earth's surface that is normally covered in one hop using F2 region is 2,500 miles, which is great. Note, just remember that F2 can take you more than 2,000 miles. Silly hint, F2, only answer with a 5 and a 2. So this is one where you kind of have to remember, you kind of have to commit some of these to memory, and that's a good one. Just remember F2 can take you more than 2,000 miles. All right. Question 10. What is the approximate maximum distance along the Earth's surface normally covered in one hop using the E region? So we've come down, right? It is 1,200 miles. Question 11. What happens to HF propagation when the luff exceeds the muff? Propagation via ordinary skywave communication is not possible over that path, and that's option A. So your lowest usable frequency has gone up and has now surpassed your maximum usable frequency. Radio communication is effectively closed. That's the way to remember that. Question 12. Which of the following is typical of the lower HF frequencies during the summer? D, high levels of atmospheric noise or static. So there you go. Summer months tend to be a little bit louder with atmospheric noise. So you might notice that the noise for your radio is a little bit higher. All right, so there we go. We finished section B. We're moving right into section C. Which ionospheric region is closest to the surface of the Earth? And that's the D region, the lowest one. And remember, we start low on the alphabet. A, B, C, D is the first layer, and then we go up from there. And that's a good way to remember it. Question 2, what is meant by the term critical frequency at a given incident incidence angle, and that is the highest frequency which is refracted back to Earth. So keep that in mind as well, that it can be helpful for trying to get out a little bit further, is figure out what your critical frequency is at a given angle of incidence. Question 3. Why is skip propagation via the F2 region longer than that via the other ionospheric regions? And it's C because it's the highest. It means your triangle of refraction, boop, boop, is at the highest point, meaning you get more takeoff angle from getting out and further away. So just remember, if your antenna has a low takeoff angle, and if you are working the F2 region of the atmosphere, you can get really far out, potentially over 2,000 miles. Question 4. What does the term critical angle mean as applied to radio wave propagation? And it's D, the highest takeoff angle that will return a radio wave to Earth under specific ionospheric conditions. And yeah, so if you're thinking of a vertical antenna, the RF comes out of it perpendicularly, and it doesn't come out straight. It comes out at all kinds of different angles. And some of those angles will be at a high takeoff angle, and some of them will be at lower takeoff angles. The critical angle is the highest angle at which the atmosphere will refract that triangle back to Earth. Question 5. Why is long-distance communications on 40, 60, 80, and 160 meter bands more difficult during the day? And the answer is C. The D region absorbs signals at these frequencies during daylight hours. The D region dissipates some during the nighttime, and it's energized more in the daytime. When it's energized, it absorbs frequencies at those lower amateur radio bands. Question 6. What is a characteristic of HF scatter? And B, the signals have a fluttering sound. Okay. Remember that. HF scatter. We're scattering our signal all over the place, and they'll have a weird audio flutter to them. Question 7. What makes HF scatter signals often sound distorted? You see, this is what you'll normally get, is you'll hear a term like scatter, and you're like, well, what is that? And you'll get something that's like, it's fluttery, like a butterfly. But then it'll give you a little bit more details as you go along, and it's D, energy is scattered into the skip zone through several different paths. And the skip zone can be like a layer or a section of the atmosphere where your signals get into it, and then they kind of bounce around inside, and then they come back down. That is also kind of a nature of the way that radio waves will traverse. Skip regions are something beyond simple refraction. It's like it gets into the super highway of the atmosphere and then bounces around and then comes down. Question 8. Why are HF scatter signals in the skip zone usually weak? And it's A, only a small part of the signal energy is scattered into the skip zone. Yeah, so it's a little bit of it that breaks into that freeway and then bounces around and then comes out randomly. And so it can be a little weak because you kind of have a weird atmospheric phenomena going on that's getting your signal there. Question 9. What type of propagation allows signals to be heard in the transmitting station's skip zone? And it's B, scatter. So you got 4 questions now that are talking about scatter. Cover your bases, learn all of them, and you'll be good to go. Question 10. What is near vertical incidence skywave, or NVIS propagation? And that's B, short distance, medium frequency, or high frequency propagation at high elevation angles. Now, it's sometimes confusing, but medium frequency and high frequency are simply different, like actual megahertz readouts of different radio frequencies, right? So medium frequency is going to be closer to like AM broadcast. Higher frequency is going to be higher frequency than the AM broadcast space. What happens is if you take an antenna, like a dipole, and you get it way low to the ground, I'm talking like 4 feet strung across, and you transmit, most of that RF is going to go almost straight up, or some of it's going to go straight up, as well as maybe a couple angles off of just vertical. And then it's going to hit the atmosphere and it's going to come back down. The issue here is that really NVIS is primarily workable from the 40 meter band and down. So 80, 160, those bands are going to be better for you for near vertical incidence skywave. You will not be able to do that with like 20 meters or definitely not 10 meters. So you need to aim for the lower frequencies to be able to make that work. Question 11. Which ionospheric region is the most absorbent of signals below 10 megahertz during daylight hours? And it is D, the D region. Now, note that you may not get D, the D region, so try not to remember just the answers. Actually look for the D region being the most absorbent of signals below 10 megahertz during the daylight hours. Okay? Hopefully that makes sense. Very good. That's one of the reasons why 20 meters is so good. It's at 14 megahertz, and anything below 10 meters is going to be absorbed, like 40 meters, right? So 40 meters, 30 meters, 10 and 20 meters are kind of like your transitionary bands that go from day to night and a little bit back and forth. But 40 is going to be better at night, 20 is going to be better at the day, and they both will work, on the opposite time, day-night cycle. But they're going to be better options, so do keep that in mind. And that is it for section G3. Hopefully you had fun with that one. That is one of the better ones, I think, particularly because I enjoy antennas so much, and I kind of love the science behind radio wave propagation. So if you are watching this is merely sub-element G3. That's general. That's what the G stands for. In you practicing for your general license. There is a playlist you can follow along below, and you can continue your amateur radio journey in hopefully upgrading your license. I hope you continue to do that. Thank you so much for watching. If you enjoyed this, give me a thumbs up. Please remember to subscribe until I talk to you again. Best of luck, and 73.